We're going to do some equilibrium calculations. It's important that you practice these so that you can recognize the language. There are kind of some subtle differences in the language. We're going to start with a relatively simple one. We're given a reaction, and we're told that the reaction vessel is charged with HI, and that decomposes to hydrogen and iodine. Now, the fact that you're not given the other two values means that the only thing that was added was HI. So the initial partial pressure of hydrogen and iodine are both 0. You know at equilibrium that the partial pressure of hydrogen is 0.0960 atmospheres. And since you initially started with no iodine, then you know that its equilibrium partial pressure must also be 0.0960 atmospheres because the stoichiometry is 1:1. And since PV equals nRT, if you have the same number of moles formed, then it will have the same partial pressure. We don't know the initial partial pressure of HI, but since we know the equilibrium constant expression, and we know the two partial pressures of the numerators of the products, which are in the numerator, and we can set that equal to Kp, we can simply solve for the one unknown, which is the partial pressure of HI. So we're going to plug in numbers, and then we're just going to solve for the partial pressure of HI. So if we do some initial algebra here, we get the partial pressure squared equals 0.0960 squared divided by 1.84 times 10 to the minus 2, which is equal to 0.500869. We continue to solve by taking the square root, and the square root of that 0.500 is about 0.70772. The units are going to be atmospheres because those were the initial units in the problem. Looks like our significant figures need to be 3 significant figures, 0.708 atmospheres. Our next problem, we have another equilibrium with hydrogen and bromine this time, forming hydrogen bromide. We're given the mixture initially is 0.682 moles of hydrogen and 0.44 moles of bromine. Those are combined, and then the system is allowed to come to equilibrium. So we can write the reaction, the equilibrium constant expression, but these need to be equilibrium values in order to plug them in and solve for Kc. This 0.682 moles in a volume of 2 liters, that is the initial concentration of hydrogen, and then 0.440 moles of bromine in 2 liter, the same reaction vessel, that is the initial concentration of bromine. And then it says at equilibrium you have 0.566 moles of HBr, so the equilibrium concentration of HBr is 0.283 molar. So it's important that you can read this problem and decide on your own that the first two values given are initial values, and that you need to divide by 2 liters, which is my volume, because the brackets mean molarity, not moles, and that this is an equilibrium concentration of HBr down here, 0.283 molar. So this is like the lab you did with the standard curve that you made, and you calculated the equilibrium constant. This was your initial introduction to ice tables. So we're going to make an ice table. We're going to plug in the values we know, 0.341 molar H2, 0.220 molar bromine, 0 molar HBr because you're not given any amount that was added to the initial vessel. 0.283 molar is the concentration equilibrium, which means you can calculate the change. Must have been plus 0.283, which means the change in the other two was half that value, minus 0.1415, because you only form half as much. And then at equilibrium, you can do 0.341 minus 0.1415 is 0.1995, 0.220 minus 0.1415 is 0.0795, and we can plug those numbers in to our Kc expression. 0.283 squared divided by the two reactant concentrations at equilibrium gives me 5.0496, lots of sig figs. If we go back and figure out significant figures, all these numbers have 3. And the only issue here is this 0.795 value, because this is the addition-subtraction rule here. 0.220 has 3 sig figs, it's accurate to the thousandths place. 0.1415 also has 3 sig figs because it comes from 0.283. That's also accurate to the thousandths place, but when you subtract those two, this initial value in the tenths place becomes 0, which means it is no longer significant because it is a leading 0. which means that this number 0.0795 is accurate to this 9, which has 2 significant figures. So our final answer should have 2. And now we're given a mole of bromine reacts with a mole of chlorine to form 2 moles of bromine monochloride. We're given initial amounts of bromine and chlorine. We're given the volume of the container, and then we're asked for the concentrations of all of the reaction components in equilibrium. We're given the equilibrium constant, Kc. And so now this case is a little bit different. We're still going to use an ice table. We're going to write in the reaction again. Bromine plus chlorine goes to 2BrCl. And these are initial values, so we're going to calculate those. This is our equilibrium constant expression. So we have an ice table. We have our initial concentrations of 3.87755 molar for both of our reactants, and then our product has 0 molar concentration. Now, since we don't know how much this changes at equilibrium, we're going to use x's in place of that. So we're going to do minus x here, minus x, and then plus 2x for the product. And that's going to give us algebraic expressions for the equilibrium concentrations, which we're going to plug into our expression for Kc. So now we're going to have an algebraic expression where we have a single variable x, and then we have, of course, an equation here, which means we have one equation and one variable, so we should be able to calculate that. So the easiest way to solve for this is to, since we have a squared term in the numerator and a squared term in the denominator, we're just simply going to take the square root of both sides, and that should eliminate the 2 exponents there. And so now we're going to move this expression to the other side. We're going to continue to solve for x, and we get this expression here, 10.259 minus 2.645, etc. X equals 2x. We're going to add this x term to both sides, 2.64, and that's going to give us 4.64x on the other side. And we're going to divide both sides by 4.64, and that's going to give us x equals 2.208. So that value for x is, remember up here, this is the value for x that we used in the equilibrium in our ice table. So we're going to plug that back in. Bromine and chlorine at equilibrium will be 3.87755 minus x, which gives us 1.669289. And then bromine monochloride is 2x, so 4.41652. And then significant figures, it looks like we have 2 sig figs divided by 4 sig figs, which gives us 2 sig figs in our molarity. Our Kc value has 2. So when we come down here, that means this number has 2. This number has 2. This 2x is exact. So now when we divide by, so here we have this 2.645 times 3.8. This is 2 sig figs times 2 sig figs, means this is accurate to this 0. This 2.645 is accurate to this 6 here. And then when we add that to this 2x, the 2x part is exact, and so it's not going to change the sig figs, so it's accurate to the 10th place. Now when we divide, this 10 has 2 sig figs, 4.64 has 2 sig figs, so our answer for x has 2 sig figs. We're going to plug that in over here. We're going to subtract. This number should be accurate to the 10th place because 2.2 is accurate to the 10th place. And then, so this is going to be 1.7 molar. And then 2x is going to have 2 sig figs, 4.4. So 1.7 molar. That should be, there should not be a 1. I don't know why I wrote a 1 there. It should be 1.7 molar. Wouldn't be 1.71 anyway. 1.7 molar and 4.4 molar. Oh, this is me going back and trying to remember that that last problem, the very first one we did, should have units of atmospheres. I forgot to tell you that. Sorry. I think I said it, but I didn't write it in the problem. So let's do the last problem. We're given initial concentrations. The reaction vessels allowed to reach equilibrium. And then you're supposed to determine the equilibrium concentrations of all 3 reaction components. And we're given the value for K. So we have the reaction equation here on the left. We have the equilibrium constant expression on the right. We're going to set up our ICE table again, initial change in equilibrium. We're going to plug in 0.35 molar on the left and 0 on the right-hand side. And we're going to have minus x and plus x and plus x on the right. So that's here. And then we're going to have 0.35 minus x, and x is our equilibrium values. Those are going to get plugged into the equilibrium constant expression. And then we're going to solve for x. So we have x squared in the numerator and 0.35 minus x in the denominator equals the value for Kc, 4.95 times 10 to the minus 4. We're going to solve for x. We get x squared. So this is 0.35 times 4.95 times 10 to the minus 4 is this 1.7325 number. And then we set up our quadratic. A equals 1, B equals 4.95 times 10 to the minus 4, and C equals negative 1.7325 times 10 to the minus 4. So what I'm underlining in green is B, and then what I'm underlining here in blue is C. So we're going to use the quadratic equation, which is shown here, to solve for x. And when you use the quadratic equation, you get two roots. These are the two roots I get. One of them is a negative number, which can't be true because that's the equilibrium concentration of our two products. You can't have a negative concentration, so that can't be true. So we're going to eliminate the second root and only use this 1.291727 times 10 to the minus 2. That means when we solve for PCl5, it's 0.35 minus x, which gives us 0.33708, which is going to round to 0.34. And then the other two are just equal to x. So if we go through and figure out significant figures, it appears we have to go through actually the quadratic equation and figure out how many sig figs the answer should have. So x is accurate to 2 sig figs, and that means in this number, because it's 0.35, it's accurate to the hundredths place. You get 0.34 molar, and you get 1.3 times 10 to the minus 2 molar. That says 0.013 molar.